So we were discussing the complexation of actinide ions with inorganic ligands. We have already covered inorganic ligands like chloride, bromide, fluoride, and also nitrate. The complexation of hydroxide I have not discussed, but that will be discussed in a separate lecture. So the hydrolysis of actinides will be covered and followed by its migration in environment. That will be a separate lecture. Now coming to the remaining inorganic ligands of relevance are carbonate and phosphate. So now these carbonates are very important because of the fact that it forms very strong complexes with some of the actinides, particularly the uranyl ion or the actinyl ion. So the carbonates form precipitation similar to the hydroxide. There are mixed hydroxy as well as carbonate of species formed, which I will be showing in the speciation diagram of uranium 6 ion, the uranyl ion. In carbonates, they form bridging complexes in these precipitates, and at higher carbonate concentration, we can have depolymerization and we have the soluble carbonato complexes. In case of the uranyl ion, the carbonato complexes, they exist at as low as pH 3 to 4.8. The different type of carbonate complexes are formed, such as UO2CO3 and trimeric species, that is UO2 thrice, OH thrice, and carbonate minus. This type of species are formed. Finally, you get the soluble complex, that is the monomeric soluble complex UO2CO3 whole thrice 4 minus, and the structure of this complex is given here. You see that in this case, all the three carbonates are forming bidentate coordination with the uranyl ion, and there in the equatorial plane, while the oxygens of the uranyl ion are perpendicular to this plane, and this is the axial oxygen. At lower carbonate concentration, this monomer UO2CO3 2 minus, as well as the trimer UO2 whole thrice and CO3 whole 6 times 6 minus, these species are formed. Now this structure of this trimeric carbonate species is given here. You can see that three carbonates are independently coordinating to the uranyl ions. So they are binding to the uranium atom in the equatorial plane, they are in a bidentate manner, while three other carbonates, they are forming bridging complexes. The bonds are bridging type. You can see that this one of the oxygen of this carbonate is actually shared by this uranium as well as this uranium, and the other two oxygens of the carbonate are binding to the uranium in the monodentate fashion. So same is there for all the three uranium atoms. Now the stability constants of these carbonate complexes are very high. As we see that this tris carbonate complex of monomeric uranyl ion, this complex is very high. The beta 3 log beta 3 value is 21.54 at 0.1 molar and 20 degrees Celsius. Now this application of this carbonate complexation that we'll be discussing in the uranium leaching from the ores by the alkaline leaching process. So in that case, you have this carbonate complexes which are making the soluble complexes from the ores, and this is coming out of the ore phase. Now, as I was discussing, this speciation diagram of uranyl ion, as you can see here, this as a function of pH, you see this at lower pH, there is a possibility of the carbonate not being stable, but at higher pH, the carbonate is stable, and it at higher pH also because of the abundance of the hydroxide ion, you also have hydroxide complexes of uranyl ion. So at very low pH, as I have already mentioned, pH less than 4, you get the only uranyl ion, and at higher pH you have the uranyl hydroxide complexes, and in the presence of carbonate you also have UO2CO3 and also UO2CO3 twice 2 minus, and at pH 10 you have pH 8 to 10 region, you have this UO2CO3 thrice 4 minus, this type of species, which is a soluble species. And beyond that, you have the hydroxide species as indicated here. Now, uranium 5 also forms the analogous tricarbonate species, similar to what I have shown for the uranium 6 uranyl ion. So that is UO2CO3 thrice 5 minus. This type of species are formed with the uranyl plus 5 species, that is UO2 plus ionic species, but then this occurs only at a very high carbonate concentration. That is, the log beta 3 value is around 13.3. Nevertheless, this is much lower than that reported with the uranium 6, that is UO2 2 plus ion. So it is more than 7 orders of magnitude lower, and the trimeric species is not from the uranium 5 because of the strong disproportions in reaction prevalent in case of the uranium 5. Uranium 4 also forms carbonato complexes in alkaline solutions. Species such as UCO3 whole 5 6 minus is reportedly formed, which has a very high stability constant. Log beta 5 value is around 40. Now, one interesting consequence of this carbonate complexation of uranium is that in seawater, uranium is present as the carbonate complexes in its soluble form. As you know that seawater pH conditions and what is the carbonate concentration prevailing under the seawater condition, that is the PCO3 concentration around 4.25. In this case, uranium exists as a soluble species, and hence uranium is present in the seawater at a much higher concentration than the other heavy metal ions like thorium. So the amount of uranium in seawater is around 4 gigatons, and it is about 1,000 times higher than that in the mines. Thorium 4 and plutonium 4, they can also form insoluble hydroxides, and if it is the carbonate concentration is very high, they can form the soluble carbonate species, but for that you need very high concentrations of carbonate, which is not available under the seawater conditions. That is why thorium 4 and plutonium 4, if it is there in the seawater, that is due to discharging of some plutonium activity into the seawater, they are forming insoluble precipitates under the prevailing conditions. Similar carbonato complexes are also formed for other actinide ions, but I will not be discussing those here. Another important inorganic complexing agent is the phosphate. The phosphates, actually they exist different species like PO4 3 minus, HPO4 2 minus, and H2PO4 minus. This depends on the phosphate concentration as well as on the pH value. The phosphate, that is PO4 3 minus, this can act as a bridging ligand and thereby forming slightly soluble precipitates of the actinide ions. At different phosphate concentrations, you can find different actinide complex species, and these complexes, they work like inorganic ion exchangers. You may be knowing some of these tetravalent phosphates like cerium 4 phosphate and zirconium 4 phosphates. They are used as inorganic ion exchangers. So similar way, the uranium 4 phosphates, they can be used as inorganic ion exchangers, and in the natural environment, the uranium 4 phosphate complexes are present in the rocks, and they can act as inorganic ion exchangers and trap different metal ions from aquatic conditions. Now the uranium 4 species like HPO4 twice 6H2O is a stable species below 9.8 molar phosphoric acid, and beyond 9.8 molar concentration of phosphoric acid, you have the species like HPO4 twice H3PO4 H2O. This type of species are formed. For uranium 6, phases like UO2 PO4 twice 6H2O, UO2 HPO4 4H2O, and UO2 HPO4 twice 3H2O. These are formed at low concentrations of phosphoric acid. Medium concentration, and now low means I mean here less than 0.014 molar, and medium and high, that is greater than 6.1 molar concentrations of phosphoric acid. Now, when you are talking about this phosphoric acid and the complexation of phosphate with the uranyl ion, there are some applications like the uranium estimation by the Davis-Gray method, where actually there is a reversal of the uranium 6 uranium 4 couple and iron 3 iron 2 couple is taking place, and that is the key of this estimation method, that is by the Davis-Gray method. And also this phosphoric acid medium, uranium which is present in the wet process phosphoric acid, this is a secondary source of uranium. Around 100 to 150 ppm of uranium is present, and from this medium also uranium separation is done. So this is another application of the phosphate complexes for uranium. Another application is the organic phosphates. This is what I was discussing, are the inorganic phosphates. Now the organic phosphates, they are very important and it will be discussed subsequently, where the extractants or ligands like tributyl phosphate, that is TBP, and dibutyl phosphoric acid, that is DBP, they are known to form complexes with the actinide ions, and as will be discussed later, this is the mainstay of the Purex process, where the complexation of uranium 6, that is the uranyl ion, and plutonium 4 takes place with TBP, and it is extracted into the organic phase, leaving behind all the fission products and all trans plutonium elements. Now other organic phosphorus compounds such as phosphine oxides, they form complexes with actinide ions to the phosphoryl group and bind to the uranium atom. So the complexes are soluble in the organic phase, and that is how the metal ion extraction is done from a variety of mediums. Now this application of this is the extraction of uranium from the wet process phosphoric acid, where a mixture of di-2-ethyl hexyl phosphoric acid, that is DEPA, and trioctyl phosphine oxide, that is TOPO, they are used as the extractant mixture. Now I will summarize the complexation of these inorganic ligands with actinides. Now this hydroxide ion I have not covered here. Little detailed manner it will be covered in a subsequent lecture where the hydrolysis of actinides will be discussed. Now the chloride, these things I have already discussed. Now you can see here I have given a range of their complex formation constants. That is for the trivalent actinides I have noted as AN3 plus. There the fluoride complex formation constants are in a range of 3 to 4, and that of chloride are less than 0.5, nitrate less than 1, sulfates 3.5 to 3.7, carbonates 4.6 to 6.3, and phosphate, that is the dihydrogen phosphate, 2.4 to 2.7. Similarly, for the actinide 4 plus ion, that is AN4 plus, the complexation constants are higher. For each of these complexing agents, you can see. Now coming to the pentavalent actinyl ion, that is AnO2 plus, the complex formation constants are in between that of actinide 3 plus and actinide 4 plus, certain cases, and certain cases like nitrate and sulfate, they becomes even less than that of the trivalent ion. Now for the actinyl 6 plus ion, that is AnO2 2 plus, the complex formation constants mostly they lie in between that of the plus 3 as well as plus 4 actinide ions. Now I come to the organic ligands. The first thing I would like to cover, the carboxylate ligands. These carboxylates, they are actually having a single charge like acetate, which is a dissociated form of the acetic acid, and it forms stronger complexes than sulfate, which is having 2 negative charges, but weaker than that of carbonate, which is having 2 minus charge as well. I have given some complex formation constants of the actinide ions in this table. You can see here the ionic strength values are given in the second column, and the log K values for the first complex, second complex as well as the third complex formed the successive complex formation. Values for all the actinide ions are given here. Now for comparison purpose, the log KH values also are given of the ligand, that is the proton association constant of the ligand is given. So that is how we can compare the complexation of the actinides with their basicity. Now coming to the trivalent actinide ions like plutonium 3 plus, americium 3 plus, curium 3 plus, berkelium 3 plus, and californium 3 plus with the acetate ion. As you can see, there is steady increase in the complex formation constants when you go in this series, that is with increasing Z, the complex formation constants increase. But there is also a ionic strength effect, but that is not that significant. When you have this complex formation constants of americium 3 plus with 0.5 molar ionic strength, you have the acetate complex formation constant log K1 is 1.99, and at 2 molar ionic strength the log K1 is 1.96. So that is very marginally it is decreasing, and same also is there for the curium 3 plus. Now coming to the actinyl ions, the 3 actinyl ions are given here are the uranyl, neptunyl, plutonyl, all in their plus 6 oxidation states, and you can see that the complex formation constant of neptunyl ion is somewhat lower than that of uranyl ion, and then for plutonyl ion it increases, as this has been the trend as discussed previously also with other complexing agents. Now there is this plutonyl ion, there is ionic strength, there is some difference as what we have been studying for uranyl as well as neptunyl ion, that is 1 molar ionic strength. However, as I have mentioned, the ionic strength effect is not that much significant. So you can say that going from uranyl to neptunial, the log K value decreases, and from neptunial to plutonyl, the log K value again increases. Coming to the propionate, compared to the acetate, it gives slightly higher complex formation constants. Propionate only have the values for the uranyl and neptunial ions. You can see that for 1 molar ionic strength, the complex formation constants are higher. That is, for uranyl, it was 2.38 at 1 molar ionic strength, and it has been increased to 2.53 for propionate. Similarly, for the neptunial ion, the value was 2.31 for acetate, which increased to 2.44 for the propionate. So that means by increasing the carbon chain length, the complex formation constant has slightly increased. That is because of the relaxation of the chelate ring in this case. And also, when we have the monochloroacetate, that case you have actually the log KH values are lower than that of acetate. That is because of the chlorine atom, which is an electron withdrawing group, and because of that the complex formation constants also are becoming slightly lower. You can see from 2.38 for acetate, with monochloroacetate it has become 1.44 for uranyl ion under same condition of ionic strength. Now the log K2 values, they become less, as it is expected, because after the first complexation, that is the second complex formation constant becomes always less because of the statistical factor, and also because some part of the metal charge is also neutralized by the first ligand. Now coming to the glycolate, which is having a hydroxide group, the values for americium we can compare with that of acetate ion. We see that the values are significantly higher, close to 1 order magnitude higher for americium and curium. And also for the uranyl and plutonyl ions, you find that the stability constant with the glycolate ion is becoming slightly lower compared to that what we have seen in case of the acetate ion. That is because of the steric hindrance which is observed for the uranyl ion, because the complexation is taking place in the equatorial plane. So the higher acetate complex formation constants are obtained with the actinyl ion, but not with the trivalent ion, and we have the just opposite trend when you have the hydroxycarbonates like the glycolate. Now also, these tetravalent actinide ions, they are stabilized by the carboxylate complexation because of the higher charge. Now finally we come to the oxalate ion complexation, and we see because of the 2 minus charge in case of the oxalate ion, the complex formation constants are significantly larger as compared to the acetate ion. See this for all this trivalent as well tetravalent as well as the hexavalent actinyl ion, that is uranyl ion. See this. Now if you have a correlation of this complexation constant of these organic ligands, that is the log K1 values with the acid association constant or the basicity constant of the ligand, then you get a linear behavior as shown here. This is for the ligands I have discussed, that is acetate and propionate. They have a very close log K1H values, around 4.76 for acetate and 4.88 for the propionate, and you find that their log K values are also more or less same. Now this type of linear behavior is there. If we have this monocarboxylate like chloroacetate, and this lactate format, they also fall in this line. But when you have this dicarboxylates like oxalate, then you find that this is falling out of this line and it is much higher. Oxalate has this log KH value close to 1, around 1.1 or so. But you find that the log K values for uranyl ion is much higher in this case. This glycolate, they form chelates, and also this oxalates, they also form chelate complexes. In case of the uranyl ion, the acetate forms chelates, but not the trivalent actinide ions. That is how the acetate complexation of uranyl ion is much higher in stability than that of the trivalent ion. Now in solutions containing carboxylates, the +4 state is stabilized as compared to the lower or higher oxidation states. Very strong triacetate complexes are formed with the actinyl ions compared to the trivalent ions. In case of the carboxylic acids with hydroxy group, the stability of the complex was found to be higher as indicated in this figure. Also, these hydroxycarboxylates have been used as an eluting agent for the intra-group separation of actinides using cation exchangers such as the DOX 50x8. As shown in the next slide, you see this elution profile of the lanthanide ions using a hydroxycarboxylate ligand, that is alpha hydroxy isobutyric acid. So here the heavier actinide is eluted first and the lighter actinide is eluted later. See the trend here. Lutetium comes out first, then ytterbium, then thulium, then erbium, then holmium, like that it goes on, and it goes up to europium. Same also the trend for the actinides I will be showing. Now for the reason for this is, for the sulfonated groups present in the DOX 50x8 resin, which is used for this separation, the heavier lanthanides are not effectively sorbed. On the other hand, the heavier lanthanides form stronger complexes with the hydroxycarbonate ligand, that is the alpha hydroxy isobutyric acid here, and hence are eluted first. Same is the trend for the actinide ions using the alpha hydroxy isobutyric acid. You see the lawrencium coming first, then mendelebium, then fermium, like that, and americium comes last out of the trivalent actinide ions. Now we go to the stronger chelating ligands like acetyl acetone, benzohydroxamate. So in these cases, we have actually the stability constants of some of the complexes as shown here in table 13. See here that the complex formation constants are much larger than what has been reported with the carboxylate ligands. And that is because of the very strong chelate formation in these type of ligands. And their application is that this acetyl acetone as well as this benzohydroxamic acid, they form these complexes which can be easily extracted into the organic phase, and that is how the separation of actinides can be done. And also this ethylene diamine tetraacetic acid or EDTA, which is a multipotent chelating ligand, and it forms a very strong complex. And you can see here that this trivalent actinide ions like plutonium 3+, americium 3+, curium 3+, berkelium 3+, and californium 3+, they form the stability constant very close to 18. Now we find slightly increase in the stability constant values with the ionic potential, that is with increasing Z of this actinide ion. Now for this tetravalent actinide ions, you find the value is around 23 to 25 as seen here for the thorium 4+, uranium 4+, and neptunium 4+. And again, compared to uranium 4+, the value is log beta value with EDTA is around 25.83, and for neptunium 4+, the value is lower, as already we have seen for the other complexing agents as well, and we have a value of 24.55. And for the plutonyl ion, the log beta value or the log K1 value in this case, because ethylene diamine forms only 1:1 complex. So this value is 16.39, which is significantly lower than that has been reported for the other actinide ions. That is because of the steric requirement of this actinyl ion, where the complexing agent necessarily has to bind through the equatorial plane. Now, in summary, this complexation of actinide is very complicated due to the different ionic species and disproportionation of the actinides. We have seen that the early actinides like uranium, plutonium, neptunium, they have multiple oxidation states and they complicate the complexation studies. And for these actinide ions, what we have to do is we have to necessarily stabilize the oxidation state in a given oxidation state and then carry out the complexation studies. For example, plutonium in the +4 oxidation state can be stabilized and then we carry out the complex formation studies such that there is no plutonium 5 or plutonium 6 or plutonium 3 present in the aqueous medium. In case of trivalent actinides, there is no such ambiguity. Mostly they present in the +3 oxidation state. However, many of these trivalent actinides are considered soft metal ions compared to the lanthanides, which are the hard metal ions. And this is the basis of the separation of trivalent actinides from lanthanides in the nuclear fuel cycle, which I will be discussing in a separate lecture. The complexation ability of the actinides, they vary in the order. Tetravalent forming the strongest complex with a given ligand as compared to the hexavalent, followed by trivalent, followed by pentavalent, and followed by the bivalent actinide. Out of the monovalent ligands or the single charged ligands, the halides generally form very weak complexes, but fluoride ion forms the stronger complexes. Same also the case for the carbonates, which form very, very strong complexes. We have seen that the uranyl carbonates form very strong complexes in the +6 oxidation state. Also in +4 oxidation state of uranium also we have seen how the log beta value is very high, around 40 for uranium 4 carbonate complex species. The stability of the complexes of hard metal ions, it is due to the very favorable entropy term, and the enthalpy terms are generally endothermic. Only coordination of highly charged anions is exothermic. So that is to say that in most of the cases for the actinide complexation, you find that the complex formation is endothermic process. And this is because of the favorable entropy term, because while forming the complexes, the inner sphere hydration is actually broken. That is, the water molecules are released and that contribute to very large entropy, and that is how the complex formation is taking place. For neptunium 4 plus and neptunial ion, that is NpO2 2 plus, the complexes are less stable as compared to those of uranium 4 plus and UO2 2 plus ions. Fluorides of tri and tetravalent actinide ions are insoluble, but those of the actinyl ions are soluble. So this is one of the very interesting observation of the actinide complexation, and this has been used for the separation science for actinide ions. Acetate forms stronger complexes than the nitrate, though both ligands have similar size and same charge. EDTF complexes are highly stable, but the carbonates to actinyl ions are much more stable. Thank you.